Um, so circular motion, you've seen a couple of lectures on that. There are really only three new things. I'm not going to go through the full description, but I'm going to try to hit sort of the highlights, and then we'll do some example problems. So circular motion. Understanding circular motion is sort of, heavily dependent on understanding the stuff we've been doing in labs with parallel and perpendicular parts of the acceleration and those adding up to the total acceleration. So I want you to, keep that in mind as you work on problems. Like channeling that stuff you've been doing in lab is an important part of making sense out of this. There are really only three new things if you take that stuff we've been doing in lab into account. It's only three new things you need to remember about circular motion. If you're in circular motion, this thing that we've been calling aparallel, what does aparallel relate to when we're doing labs? It relates to changing speeds. Okay, so if the speed is changing, then you have an aparallel. If the speed is increasing, it's in the same direction as the velocity. If it's decreasing, it's in the opposite direction of the velocity. In circular motion, aparallel has a new name. It's called tangential acceleration. And I'm going to call it A tan, it's a vector. So that's the tangential acceleration. If it were up to me, I would just keep calling it aparallel. I made up the name aparallel, but I wasn't born early enough to decide what we call stuff for circular motion. They'd already come up with that, so I just have to use what they use, But there's nothing different about those. So just remember, tangential acceleration is what we've been calling aparallel. Aperpendicular, what we've been calling aperpendicular, what does that relate to with our lab stuff? Turning, yep. And that's still the case, but now we're going to call, for circular motion only, we're going to call it centripetal acceleration. And I'm going to use the notation A-cen for that part. Okay. Centripetal, by the way, means toward the center. So one thing that makes this easy with circular motion is that centripetal acceleration, that part that's perpendicular to the velocity, always points right toward the center of the circle. And then the last new thing is if something is in circular motion, the magnitude of that centripetal acceleration is always known. You can always calculate that. And that's equal to the speed squared over the radius of the circle. So this is the magnitude of the centripetal acceleration vector. And capital V is the speed of the object. r is the radius of the circle. Okay, this equation doesn't work for any other kind of motion except circular motion, but it always works for circular motion. So that's a nice bit of extra information that we have. One way you can think of circular motion is it's the motion where the speed over the radius is equal to the magnitude of your perpendicular acceleration. That's like a defining thing about circular motion. We're going to divide up the world of circular motion problems into two separate types. One is tetherball type problems, is what I called it in the lectures, and that's just where you have a horizontal circle and the thing is supported only by a cable or a string or a rope or whatever, and then everything else. Oh, I read this stupid joke yesterday. You don't have to pretend to think it's funny because it's almost offensive. It's so stupid, but still it's important for understanding circular motion. So, what? No. It's still a lead in. It's a long lead into this joke. Okay, I'm telling you the joke right now. Did you know that the inventors of the Ferris wheel and the merry-go-round never met each other? They travel in different circles. It's not funny. Okay, but here's why it's important, okay? Because there are two kinds of circular motions that we're going to deal with. Let's say there are two orientations of circular motion that we'll see. And here they are. Here's the sky. That's the sun. Here's the ground. That's a flower. There's circular motion like this, like a Ferris wheel. And there's circular motion like this, like a merry-go-round. Okay. I'll call this one like vertical. And I'll call this one horizontal. And then besides saying those words, I'll indicate with my hands, gesticulate. But the thing is, you always, in every one of these problems, pretty much every one of these problems, you're going to have to make the distinction between which of these you're dealing with. And the reason for that is gravity has a different relationship to each of these, In these vertical circles, gravity is in the plane of the circle. And in these horizontal ones, gravity is out of the plane of the circle. And so you're going to have to deal with gravity differently in those problems. Okay? I mean, there are infinitely many orientations of circles. Say if this is, this is horizontal. You could have any orientation on the way to, like the Enterprise at Valley Fair, where you start out going horizontal and then it tips you up. There's all those circles in between when you're going like this and going like this. We're just not going to do those calculations in this class, but they all have various relationships with gravity, if you know what I mean. Okay, so I'm going to start out by giving you a set of steps. Which way? This way? Tetherball problems are easier to deal with their own kind of approach. We'll talk about that after. Every other kind of problem besides tetherball problems, you're going to approach sort of the same way. Okay, so I'm going to start by giving you a general set of steps for everything that's not a tetherball problem. So here are the general steps for circular motion problems except tetherball problems, and those I'll talk about on their own. So the first step is, so you see a problem, you recognize that it's not a tetherball problem, and so now you're in this set of steps. The first thing you want to do is choose a view of the problem where you're looking at the circle, where you can see the circular shape of the motion. So let's say where the path looks like a circle. Okay, so like in these two pictures I drew up here, if you're doing a vertical circle, then that's the view that you want to take because you can see that circular shape. If you're doing a horizontal circle, you don't want to take a side view like that. You can't see that the shape is a circle. You want to take a view from above. You know, then you're looking down on the circular motion. Okay. Second, choose an instant to isolate, to analyze. So that's like a point on the circular path. You know, so if this is the circular motion, you're just choosing some point like this. Okay. Third, draw the vector ascend, the centripetal acceleration vector, from the object toward the center of the circle. And remember that the magnitude of this is speed squared over r. Okay. So if you're, so like in that example above, here's your centripetal acceleration vector. The magnitude is v squared over r. If you know v, if you know the speed and the radius of the circle, you can come up with that full centripetal acceleration vector. Okay. Fourth, this one sometimes you do and sometimes you don't. If the speed is changing, in other words, if it's non-uniform circular motion, then draw the tangential acceleration based on whether it's speeding up or slowing down. This is just like the stuff that you did in lab. now that you have the centripetal acceleration, which is always there, and you have the tangential acceleration in the case that it's there, sometimes it is, sometimes it isn't. Now the total acceleration vector is just the sum of those two parts. You might know these as numbers. You might still have variables mixed in that you'll have to solve later. But at this point, you have an expression for the total acceleration vector. And then the last steps are draw a free body diagram and use Newton's second law. Okay. You'll almost always have to do all these steps. Sometimes, like this first example problem I'm going to do, we're done once we get to step 5. Okay. All right, so I'm going to start with a couple of uniform circular motion problems. What does that mean, uniform circular motion? Non-uniform means the speed's changing, so uniform means the speed's not changing. So with uniform circular motion, you don't have any tangential acceleration. There's no perpendicular part to that acceleration. Okay, so the first example, you know those things, I really should look up what these are called. It's been like 15 years and I always just describe it like this, but like in any comedy that has astronauts in it, at some point there's a scene where they put them in that chair and spin them around in that circle. I think it trains people to deal with high G-forces. I don't remember what it's called, but it's a long thing and the person sits here and then like in the movies they like make faces or possibly pass out and everyone laughs. They don't wear t-shirts, but I don't know how to draw astronaut stuff. Okay, so they're going in a circular path like this. So let's say that the length of this arm is 4 meters. And let's say that this is uniform circular motion. So we're just talking about this thing getting up to speed and then staying at a certain speed. How fast does the person have to move? You know, how fast does the speed have to be? How, you know what I mean? How fast does the speed have to be for the person to experience five G's? Okay. So say that that's your, you have this contraption and that's this training, that's what you want to get them up to. So how fast do you have to make this thing go? Well, first of all, 5 G's means a magnitude of acceleration of 5 times lowercase g, which is 5 times 9.81, so 49.05 meters per second squared. Okay, so that's the acceleration magnitude that we're talking about. So let's start going through the steps, and we're going to get to the end of this problem before we get to the end of the steps. But so here's the circular path, and I'm going to just use the usual coordinate system like this. And we have to choose an instant to look at. It doesn't matter what instant you choose, but I guess I'll think of it over here. The centripetal acceleration vector points from the person toward the center of the circle. The magnitude of that acceleration is speed squared divided by r, which we know is 49.05 meters per second squared. That's what we want. What's the radius of this circle? 4 meters, yep. So this equation says v squared over 4 is equal to 49.05. So v squared is equal to 196.2. Take the square root and you get that v is equal to plus or minus. I didn't write this down. Can someone take that square root for me? I have a calculator, but I'm lazy. I just forgot I had it, that's all.
14.007.
Okay, so let's call it 14.01 meters per second. This is a speed. Speeds are always positive. So somewhere around 30 miles per hour. At that point, with this arm that's 4 meters long, this person would be experiencing 5 Gs of acceleration. Any questions about that? Okay, I'm going to do another uniform circular motion problem. So let's say we have a 1,000 kilogram car. Moving around a circular section of a track. Bless you. At 30 meters per second. The radius of that section of the track is 50 meters. So one thing here is that, you know, the track might be shaped like this, but it doesn't matter whether the whole path of the object is a circle. It just matters that at the instant you're looking at, it's moving in circular motion. And so this radius is 50 meters. So let's calculate two things. First, let's calculate the total acceleration vector. And second, let's calculate the net force. Is this uniform or non-uniform circular motion? Yeah. And you know that because I said specifically that it's uniform circular motion. But you also would know that if I hadn't said that because it says, oh, well, I didn't say it, that this is at a constant speed. I should have said it. So anytime it says that something's happening at constant speed, you know that's uniform circular motion. Okay. Okay, so let's draw the path. And even if the full path isn't a circle, at this instant, we're going to think this, like at the instant we're looking at, the object is in circular motion, and that's the circle we're going to draw. Okay. And then choose an instant to do the calculation for. I'm going to choose the one that I drew up above. So that's where the car is at this instant. And I'm going to imagine it going around the circle this way. And I'm just going to use the usual coordinate system. Okay, so the centripetal acceleration points from the object toward the center. Okay. And the magnitude of that centripetal acceleration is the speed squared divided by the radius. So that's 30 squared divided by 50, or 18 meters per second squared. That's the magnitude, but we need to put that into a vector. So notice that that is pointing in the negative x direction. So the centripetal acceleration vector is negative 18, 0. So the total acceleration vector, you know, is always the centripetal plus the tangential, but in uniform circular motion, there's no tangential. And so the total acceleration is just the centripetal. And so the total acceleration is negative 18, 0. So that is part A. That's the acceleration vector. How many g's of acceleration is that? A little less than 2, yeah, right about 2. Right, just 2 times 9, you know. And now we want to calculate the net force. Well, normally if we're calculating forces and using Newton's second law, almost always we have to draw a free body diagram. But if you're just calculating the net force, there's no need for the free body diagram, because on the free body diagram, you're just putting the individual forces, right? Newton's second law just says F net is equal to mass times acceleration. So in a case where you're just trying to calculate F net, you can just plug it right into this equation. A free body diagram doesn't help you with anything. So F net is equal to the mass, which is 1,000 kilograms, times the acceleration, which is negative 18, 0. And so F net at that instant is equal to negative 18,000 newtons, and then 0 for y. And F net then is made up of all those individual forces, but we didn't have to deal with that in this problem. Any questions about that? Okay, so now I'm going to do a non-uniform circular motion problem. So let's say now we have so this is non-uniform circular motion. This is a vertical circle, like a couple of the problems from the lab this week. So you have a mass swinging around on a string. That hand looks way better than my one yesterday. You guys are lucky. You got to see something really special happen here today. Okay, and this thing swinging around this way. And let's say that the ball has a mass of 0.1 kilograms. And the string has a length of 0.2 meters. And let's say that, so for part A, at this instant, let's say that we know the tension in the string is 80 newtons. How would you know that? By the way, is there any way to know that? You know, you could have some kind of force measuring device at the end of the string that's measuring it, or you could have a spring and measure how long the spring is, and that would tell you the force, you know, like a fish scale kind of thing. So say that at this instant, you know that the tension in the string is 80 newtons. The question is, how fast is the ball moving at that instant? And then second, calculate the acceleration vector. Is this a tetherball problem? It's close, but a tetherball problem just has to be horizontal. So this is not, so we're going to use the other approach. So draw the circle, choose the instant to look at. In this problem, that's given for us. So I'm going to do it over here. I'm going to use this same coordinate system I always use. The centripetal acceleration goes from the ball to the center of the circle, toward the center of the circle. So it's this way. magnitude of that centripetal acceleration vector is speed squared over r. Do we know the speed or the radius? Right, exactly. We're trying to calculate speed. The radius is 0.2. So this is v squared over 0.2, which if you divide by 0.2, that's the same as multiplying by 5. So. And so we can use this to come up with the centripetal acceleration vector. Notice that's pointing in the negative x direction. So this is negative 5 v squared, 0 for y. So we don't numerically know the centripetal acceleration vector, but if we calculate v, we'll be able to plug it in and then we'll know it. This is non-uniform circular motion. So now we also have to account for the tangential acceleration. This is the first one of these problems today where we've had to do that. This ball is on the way up. So from lab, do you remember, does that mean it's speeding up or slowing down? Or from living on Earth and having noticed this? Slowing down on the way up, yep. So the velocity is this way. So which way is the tangential acceleration? Opposite, yep, down, exactly. We don't have a way to calculate the tangential acceleration. We will see that we do have one when we get to Newton's second law, but for now all we can say is we have this variable that I'll call a tan, and it's in the negative y direction. Okay, so the tangential acceleration vector is 0, negative a tangential. I'm sorry if that's a little confusing. I'm using this a tangential to represent the vector, and then it's also just a variable that's in there. You could give those different names if you prefer, you know. But what this says is if we know this variable a tangential, we can plug it in and it'll give us the tangential acceleration vector. Okay, so now we can put these together. The total acceleration vector is these two vectors added together. And so it's negative 5 v squared 0 plus 0 negative a tangential and so we can represent this acceleration vector as negative 5v squared for the x component, negative a tangential for the y component. And we don't know any of this stuff. So now we have an expression for A. If we can figure out A tan and V, then we'll have a numerical value for acceleration. But this is all we have so far. Okay. So now that we've gone as far as we can with the acceleration, now I'm going to draw a free body diagram and use Newton's second law. Okay. The first thing we're trying to figure out is the tension in that cable. So free body diagram. Of the ball at that instant, there's a weight force down. That's 0.1 times 9.81, so that's 0.981 newtons. Then go around the boundary looking for contact with the surroundings. The only contact is the string. That's a pulling force, and so the rules are parallel to the cable at that instant, away from the chosen body, and that force is T. So at some point we're going to have to plug in the 80 for T. We could do it here, or we could recognize it later, you know. I guess I'll just leave it like this for now. So now go to Newton's second law and add up these forces. Is that T in the positive or negative x direction? Negative, so we have negative T0 plus, is this 0.981 in the positive or negative y direction? Yep, so 0, negative 0.981. And all that's equal to the mass, 0.1 kilograms, times the acceleration. And so we'll put in what we know about the acceleration. It's negative 5v squared for x, negative a tan for y. And so we get two equations. The x equation says negative t is equal to negative 0.5 v squared. And the y equation says negative 0.981 is equal to negative 0.1 a tan. Well, from the x equation, we can see that negative, so now I'm going to plug in that 80 that we know is the tension in the cable. So we have negative 80 is equal to negative 0.5 v squared. So 160 is equal to v squared. So v is equal to plus or minus, take the square root of 160. So plus or minus 12.65 meters per second. This is a speed, so you only ever have positive speeds. So maybe just under 30 miles per hour to get a force that big. So that's the answer for part A. And now for part B, we want a numeric answer for the acceleration at that instant. We have these two equations, and we have that the acceleration is, this is the total acceleration vector. All we need to do is fill in those variables. Okay. So first, so I'm going to write this again. So A is equal to negative 5 v squared, negative a tangential. We know now that V is 12.65. The y equation from Newton's second law says, negative 0.981 is equal to negative 0.1 a tan. So we can multiply both sides by 10, and we get 9.81 is equal to a tan. I guess multiply by negative 10 to get rid of that negative. And so now we can just plug these into our acceleration expression. And this acceleration vector is negative 800 for x, and negative 9.81 for y. So if that ball had like a gerbil inside of it, that's how uncomfortable it would be. That's, you know, that's around 10 Gs. I don't know, I bet actually squirrels, because they're little, I'll bet they can handle a lot more Gs, to be honest. So maybe it'd be fine. Anybody have any questions about those steps? Yeah. About gerbils or the... Okay, because I was just, so starting from this y equation, I was just trying to solve for that variable A tangential. So I'm just doing the algebra to get that. Any other questions? So if you can look at these 3 example problems and the other ones in the notes and stuff, and sort of spot the similarities in the approach, even though like different questions ask for different things, but you can sort of start them all the same way. And once you sort of are comfortable with those similarities, these problems will, not be very tricky. I think at first circular motion stuff feels kind of tricky because of the new terminology. So it's not totally ingrained in your head yet what the centripetal and tangential acceleration are. But remember, that's nothing hard. That just takes time to get used to it, Okay, so now tetherball problems. Okay, so a tetherball problem is a problem with a horizontal circle where the object is only supported by a cable or a string or a rope or whatever, a chain. So okay, so if you could also have problems where there's a cable and the thing's rolling around a table or something. That's different because there's that second force that would be the pushing force from the ground or the table. So the only support for these kind of problems, this is the approach if the only support is a cable. Tetherball problems are always uniform circular motion. So that's the good news. With the assumptions that we're making, which is that this cable doesn't have any mass and there's no friction or anything, there's no way for this to be anything but uniform circular motion. And so for this, the first 2 steps are different. So for these, the first two steps are different. So step one, the main difference is instead of taking a view where you can see the circle, which would mean looking at it from above, in this case, we're going to take a side view. So so we're going to take a view like this, and this is the coordinate system. Okay. This is the length of the cable. The radius of the circle, like notice that that ball isn't swinging at an angle, it's swinging horizontally. And so the radius of its circular motion is actually just that horizontal lower leg of that triangle. So R is this, and it's just equal to L times the cosine of theta, where this angle is theta. Okay, so that's always true. And now to draw the centripetal acceleration, now we're back on the rest of the steps. It's pointing from the object toward the center of the circle. You calculate it the same way, and everything else is the same. Okay. Okay, so let's say we have a problem like this. This object's traveling in a circular path like that. Okay. And the angle that this thing makes with the horizontal so I'm just going to represent that on the picture as theta. And the length of the cable is 2 meters. And the mass of the ball or the object is 1 kilogram. So first, I'm going to do this in 2 parts. I'm going to first do it like numerically, where I give you a value for theta, and then we're going to do it generally in terms of theta and see how that angle changes with speed and how the tension changes. So let's first say if theta is equal to 30 degrees, what are the speed, V, and the tension in the cable? And then second, we're going to calculate the speed and tension for theta generally. You know, we're just going to use that expression theta and use that to see the relationships between theta, V, and T. Okay, so for part A, there's the view. This angle is 30 degrees. This length is 2. The radius of the circle is 2 times cosine of 30. Which is 1.732. The centripetal acceleration points this way. The magnitude of that centripetal acceleration is v squared over r. We don't know v, but we know r, so I'll write this as v squared over 1.732. I'm going to use this usual coordinate system. So the centripetal acceleration vector is, notice that that's in the negative x direction. So we have negative v squared over 1.732 for x and 0 for y. Is there tangential acceleration? No, because it's uniform. So the total acceleration is just equal to the centripetal. And so it's negative v squared over 1.732 and then 0 for y. We can't figure out any more about the acceleration without using Newton's second law, so let's draw a free body diagram. We have a weight force acting down of 1 kilogram times 9.81, so 9.81 newtons. And the only contact force is the pulling force from the cable, so it's that way. I'll call it T. So now we're going to go to Newton's second law. Before I do that, let me just figure out the components of this force. So we know it has a magnitude of T. We know that this angle is 30 degrees. So what's the counterclockwise angle from the positive x-axis to that force? What? Yeah, 150, right. So this is T times cosine of 150, T times sine of 150, which is negative 0.866 T, positive 0.5 T. And so now we can write out Newton's second law. We have that cable force that we just figured out, negative 0.866 T, positive 0.5 T. Plus the weight force, 0, negative 9.81. is equal to the mass, 1 kilogram, times what we know of the acceleration so far. So that's negative v squared over 1.732, and then 0 for y. So we have two equations. The x equation says negative 0.866 t is equal to negative v squared over 1.732. And the y equation says positive 0.5 t minus 9.81 is equal to 0. Well, this is just a system of two equations for two variables. We can use the y equation to solve for t and then plug that into the x equation. So this says 0.5 t is equal to 9.81. Multiply both sides by 2, and you get the t is equal to 19.62. Then plug that into the x equation, and you get negative 0.866 times, so now I'm plugging in 19.62 for t, is equal to negative v squared over 1.732. And you get v squared is equal to 29.43. Take the square root. And you get v is plus or minus 5.42 meters per second. Take the positive one because it's speed. Okay, so this is the tension in the cable, and this is the speed. Okay, nobody wants to do the second part of this, so let's just talk about it instead, okay? So if this thing is spinning around at 5.42 meters per second, say 12 miles an hour or something, that angle is 30 degrees, and the tension in the cable is 19.62 newtons. If it's spinning faster, what do you think would happen to that angle 30? Would it get bigger or smaller? Smaller, yep. And what would happen to that tension, do you think? Larger, that's exactly right. Okay, so if you spin that thing around faster, the tension in the cable gets bigger, it gets closer to horizontal. Do you think it could ever get to be horizontal? No, that's like a limit, you know. You could never get it going. It would take infinite speed for that to get horizontal, okay? And that would be infinite tension, and it would be a whole mess. So you can't get there. But, you know, so, and if you wanted to do it without doing it with the variable, you could plug in 0.1, an angle of 0.1 degrees and see how fast it had to be spinning or something. And the answer is something like 200 some miles per hour. And if you put in 0.05 degrees, it would be 1,000,000 miles per hour, you know, but it can't ever be horizontal. That string always has to be hanging down at least a little. Okay, that's all. Hi. That is 1 divided by 0.2 is the same thing as times 5. Yeah, here. You know, like dividing something by 0.2 is the same thing as multiplying by 5. So I just sort of simplified it. But you could have left it as divided by 0.2 and it would have been fine. Sure. Hey. Oh, yeah.